Welcome back to the last lecture in Chapter 11, and probably the last lecture of General Chemistry 1 for this Summer 1 semester. We're going to continue on our discussion on bonding theories, way chemicals bond together, or way elements bond together. And so what we're going to look at is what's known as the valence bond theory. And this is one of the two advanced bonding theories that we're going to look at. It helps explain bond length in both natures, wave and particle, of electrons with these advanced bonding theories. This one, the valence bond theory, states that electrons still reside in their orbitals, right? And this is going to be compared to the next one where it's they're not really going to reside in their orbitals, but we're going to make different orbitals. We'll talk about it when we get there. But what we're going to look at is we're going to talk about hybridization of orbitals. Now, what do we like? Why do we need this? Right? I mean, that's the question: is why do we need this? And I want to show you on the board why we need this. So, on the right side, as you're looking at the screen, or maybe it's on your left, you'll notice two hydrogens, the electron orbital diagram, or the orbital diagram of two hydrogens, and sulfur. It's a little crowded, I apologize, but so we have hydrogen, and then we have sulfur. Now, judging from this, it's pretty easy to see that to make H2S, right, this electron can go there, and this electron can go there, into that free one, right, and all the orbitals are filled, they're happy, we now have H2S. But what we see, and why we need to talk about orbitals, is the example of carbon. Let's go move my camera over just a little bit so you can see that. There we go. It is carbon, right? So we have CH4, let's say. So we want to make CH4. So we have 4 hydrogens, right, with their 4 electrons, and then we have carbon. Well, we can easily see this one would go here, and this one would go here. Oh, well, but then where would the other two go, right? There's no other carbon electrons or electrons for carbon that those hydrogens can bind to, right? And so there's no covalent bond formed because there's no free hydrogen, or at least free electrons, at least currently written like we wrote it. And so what we have done, and what scientists have done, is saying, well, hey, what would happen if that S hydrogen, or that S hydrogen, man, I'm just messing up my words. If that S orbital and this P orbital were to combine and hybridize into what's known as an sp orbital, we would have 4 of them, right? 1, 2, 3, 4. And there would be 4 electrons in there because we just took these 2 and these 2 and we spread them out in this new thing that we made. And now we have a place for all 4 hydrogens to go to. And so what we're going to see is that's actually more than likely the way that bonding works. And so I'm wheeling back over to my computer so we can get the PowerPoint back on. And so the hybridization of atomic orbitals is common in valence bond theory, right? And it helps to describe what is happening with other molecules, like we saw with the carbon over there. Hybridization is the mathematical procedure, right? So it's a mathematical procedure in which standard atomic orbitals are combined, right? Because we talked about getting orbitals. We get orbitals through the Heisenberg uncertainty equation, right? And or sorry, not Heisenberg's, but Schrodinger's equation, right? Where it's a calculation, we get these quantum numbers. So mathematically, what we can do is we can combine these hybrid. You don't have to know how it's done. We just have to know that it is done. And so what happens? And here in the picture, we're looking at what happens with carbon that we saw on the board, is that what they've taken is that S and the 2p the orbitals, and we've made hybrid orbitals. We'll talk about sp3 orbitals in the next slide. And so what does it mean to be an sp3 hybridized orbital? This is the complete hybridization of the s and p orbitals. And so the way we can remember this is there's one s and 3p, right? So if you see sp3, then you know all 4 orbitals are, all s and all p orbitals have been hybridized together. And this is kind of what they look like. It lends to the angles that we see with the tetrahedral arrangement. And here you can see there's 4 electrons that will pair with the electrons from hydrogen. So this is sp3. There are 4 total orbitals in an sp3 hybridized thing. So if you see 4 things around a central atom, you know that it is sp3 hybridized. It has to be. We'll talk about maybe how we can determine what is what. I think I have an example on here. If not, we'll go to the board and make one. All right, so sp2 hybrids. So let's say we don't want to hybridize all of the s or all of the p orbitals with our s orbital. And so here's an example where we can just take 2 of the p and 1 of the s and hybridize into sp2. And so sp2, there are 3 hybridized orbitals, but there, as you can see on the picture, there's still an unhybridized p orbital. And what that unhybridized p orbital is for the production of a double bond, right? So that electron will pair with another unpaired or unhybridized p orbital to form that double bond. There are, so because of this, we can name bonds differently. A single bond. So if you look at the 1,2-dichloroethane, if you look at the middle there, that is known as a sigma bond, right? Single bonds are usually known as sigma bonds. Around sigma bonds, we have free rotation, right? That very loose, right? That those things can just spin, those molecules. But if we had a double bond, we talked about double bonds, making double bonds with the Lewis structure analysis, that comes from an unpaired or unhybridized p orbital. And what happens though is if you were to take a double bond, so right now we have 2 bonds, we cannot turn this as easily as we could just turn this, right? And so we've kind of locked into place our structure. These are known as pi bonds. So if on an exam I were to say this at what hybridization does this atom have? If you see a double bond, you should say at least it's an sp2, right? At least it's an sp2. If you don't see a double bond and there's 4 things around it, you should say, that's an sp3. Let's look at sp now, right? So sp hybrids can form triple bonds, right? So we now have, between the s and the p, we have 2 hybridized orbitals. And then between the unhybridized orbitals, we now have 2 p's that are there. And so we can now form a triple bond, like what we talked about before. And here is here's ethine. And so because there's 2 pi bonds. So if you see something that has 2 double bonds to it, or you see something with a triple bond, you know that it has to be sp hybridized. It's sp hybridized. So now we talked about when we talked about Lewis structures that there are some molecules out there, some elements that we can turn that around the right way, that we can expand their octets, right? So that instead of going just, having an octet, we can have 10, right? We can expand those octet. And so we're going to look at that. And these are things that have access to the d orbital, right? These compound, these elements have access to a d orbital. And so what happens, and usually we can do this where we see how many things are bound to it. And so here in this example, we see arsenic pentafluoride. And so what we see is arsenic pentafluoride. We know that arsenic is bound to 5 things. So we need 5 orbitals, right? We need 5 hybridized orbitals. Well, we get sp3, so there's 4, but we need a 5th. Well, there's a D, right? There's a D that's available. And so we just put that D in. And so now it's sp3d. There's the 5. And then if we have 6, if we have the octahedral arrangement, sulfur hexafluoride, right? So now we need an extra one. So we just take another one from the D. So we have sp3 d2, d2, and so that gives us 6 orbitals that we're able to bind with, right? And so hybridization, we should be able to look at something and determine its hybridization status. Let's go back to the board and let's take a look at that. And then what we'll do is I'll say one more thing about hybridization, and then we'll go on to the very last thing that we need to talk about. So, and I will help with this. Right, so there's an organic molecule. This is acetylaldehyde, right? And so what I would like you to do, it's gonna move over, is I would like you to tell me how many sigma bonds there are in this molecule and how many pi bonds. All right, I lost my other color of marker. Let's see if this one works. All right, so sigma bond is here, 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 and here, right? So there are 1, 2, 3, 4, 5 sigma bonds, right? Because remember, sigma bond is just meaning a single bond. And then there's there's one pi bond. There's another sigma bond, right? So when you have a pi bond, that other bond of the double bond is a sigma bond. Wow, I missed. So there are 6 sigma bonds, 1 pi bond. So then what I want you to tell me is what's the hybridization around this carbon? We'll call it A, and this carbon, we'll call it B. Okay, so around carbon A, it's going to be sp3, right? Because it's bound to 4 different things. So we need 4 hybridized. We need 4 hybridized orbitals. So that's sp3. B is the giveaway. Remember, is the double bond. Oh, it's a double bond. It has to be at least an sp2. And so it's single, double. It's going to be an sp2 hybridized orbital. So what we can do with these, though, is that there are geometries associated with these hybridized orbitals. So with the sp, you have linear. With the sp2, you have trigonal planar. With the sp3, you have tetrahedral. With the sp3d, you have trigonal bipyramidal. And with the sp3d2, you have the octahedral. And you will need to know that. You will need to know the geometries associated with the hybridizations. That way, if I were to say, what is the geometry around an sp3 hybridized carbon, you could say, ooh, that's tetrahedral. So we just need to know that. So so there's one more theory that we're going to talk about in the last few minutes, and that's the molecular orbital theory. It's another advanced bonding model. What we're going to do is we're going to make our own orbitals for bonding, right? We're not going to use the typical orbitals that we're used to. And then what we're going to have to do is we're going to have to calculate the energy. We're going to then do one more step to make sure that our prediction is correct. And so what we're going to do is we're going to look at what's known as bonding and anti-bonding orbitals, right? And so the bonding orbital is the electrons occupying this orbital are less energetic than their atomic orbitals. The anti-bonding orbital is more energetic than their bonding orbitals, or their atomic orbitals. What we see is with the bonding and the anti-bonding deals with the destructive and the constructive interference that we talked about before with waves, right? That if they're in the same wavelength, if they're in the same pattern, they're going to be constructive. If they're going opposite direction or the opposite waves, then they're going to be destructive. And that's what we see. With the anti-bonding, it's destructive. With the bonding, it's constructive. So how do we do this? Right, so I'm going to show you a picture here, and I'm going to show you what we need to calculate, and then we'll look at a couple examples, and then we will probably be done. So we can draw molecular orbitals. right? And this is what we're talking about. So let's look at hydrogen. So hydrogen makes H2, right? So we have hydrogen. So each one has one electron in the s. So we're talking about just the s. So we have a sigma, which is the s, right? Sigma 1s, sigma star 1s. That star just means it's anti-bonding. The sigma just means it's bonding. And then what you do is you say, okay, I have 2 electrons. We start at the lowest level like we did before, and then we just fill our way up. And so here, H2 molecule, both of them are in bonding. How do we know if this prediction is correct? How do we know if this is actually true without actually knowing that it's true? And what we see is what's known as bond order, right? It shows the amount of electrons available to bond the 2 molecules together. And a positive number, it's stably bond. Negative number, or 0, means it's unstable and it usually will not form or cannot form in nature. So let's go ahead and just do one more. We'll just look at p orbitals, right? Because p orbitals can take place in bonding, where we have sigma bonds and pi bonds. Very slightly different than what we talked about before with sigma bonds and pi bonds. But nonetheless, we can use those. So what we're going to look at is we're going to look at 2 things before we go. Let's see here. Stop the share. All right, we're going to look at 2 things before we go with these bonding orbitals, these molecular orbitals. Okay, we're going to look at one thing. We're going to look at why, right? So helium, right? Helium is a noble gas, and it's usually a monoatomic element, right? So it's just helium. Why? Right? Why? So let's look. So helium, we have 1s, 2 electrons. 1s, 2 electrons, helium, right? And the way we do these molecular orbitals is we usually put the compound that we're going to try to describe down at the bottom. There's our sigma s, right? There's our bonding orbital for the s. Sigma star s. There's our sigma for the antibonding. And then what did we say we do? We start filling in from the bottom. We have 1, 2, 3, 4. All right. Now let's look at bond order. Right? Bonding order is equal to sigma, the number of electrons in the sigma molecular orbital, minus the number of electrons in the sigma star molecular orbital, divided by 2. Right? Because we're just looking at 2. We're taking the average of the electrons in the sigma, or the bonding molecular orbital, and the minus the ones in the antibonding orbital. So let's look at this helium. We have 2 minus 2 divided by 2. 0 divided by 2 is equal to 0. And if something equals 0, that means it cannot bind. It will not bind. It's very, very unstable. And so helium-2, He2, cannot be formed. And this is the explanation to why. I want you guys to tell me, there's 2 things I want you to tell me. And I want you to try to do this. I'll show you one, and then I want you to do a couple other ones. So let's look at oxygen, right? So let's look at oxygen. Oxygen is 6. So we have 2s, and then we have 2p. There's 6, right? 2, 4, 6. Oxygen. So we have 2s, up, down, 2p, and this is oxygen. And I want to make O2 gas. What we find with regards to these pi bonds and these other orbitals, it really depends on what we're looking at. And actually, I drew these 2 things really close together, so I'm going to back them up a little bit, or spread them out a little bit. Right? So when we talk about adding in that p orbital, this is what it looks like. So we saw this before with our helium example, right? with the sigma s and the sigma pi s. Now, it's really interesting with regards to which element we're talking about, but we're just going to do it the same way. We now have a sigma p. These are known as pi p. This is pi star, right? Because those are antibonding. Sigma star p. Right, so it's the same layout. We're just adding a little bit more because we have more things to add. So let's start filling in. We start filling in from the bottom. So there's our 4 there. And now how many do we have up here? That's right, we have 8. So there's 1 or 2, 4, 6. And remember, they're degenerate, right? Or we have to fill them out like that. There's 8. All right, so now let's look at the bonding order just to make sure. So we do all of the ones that are in the bonding. So we have 2, 4, 6, 8, minus the ones in the antibonding, 2 and 4, divided by 2. So it's going to be 4 divided by 2 is going to be 2. So obviously O2 forms. You can't see it up there, but it's 8 minus 4, right? Because there's 8 total electrons in the bonding molecular orbital. There's 4 in the non-bonding or in the antibonding. Now, the question I want to ask you, is this paramagnetic or diamagnetic? So remember para and dia and what those mean and whether they can be done, what kind of influence the magnetic field has on it. And so what I want you to answer that question for this one, is this para or dia? And then I want you to look at O2, O2 2 minus. I want you to look at that and then answer the same question. Is it para or dia? Well, that ends this lecture for chapter number 11. If you guys have any questions, again, just reach out and ask, and I will be sure to answer them.